Okay, so we finished the one exercise to apply the idea how about the cooled flow in our real case. And the second exercise also related to the cooled flow. But the condition is different because right now we have some incline angles to consider how about the force balance between the weight, gravity weight, and the shear stress force. Okay, so that's again we are trying to understand what's the problem. So the first, you see a ball. We have the ball plate. It's a 1 by 1 meters square, the areas, and put on the incline. Tables, okay, and the incline table with the theta showing here is 20 degree. So for these problems, we write down some information we already know. We have the plate, right? This is a plate, and with the area is the 1 meter multiplied 1 meter is equal to the 1 meter square. Okay, this is our plate areas, and we just put on the incline tables, and the incline angle theta here is 20 degree. And that we already know the plate with the constant velocity is 2 centimeter per second. So we have the constant velocity, okay, it's v equal to the 2 centimeter per second, and we convert the unit to meter, 0.02 meter per second. Okay, and we know that we put the oil as the lubrication material between the incline table and the plate. And we know that the oil, the viscosity for the oil, mu, we have the number is 0.05 Newton seconds per meter square. So we actually the question tell you assume that the oil can be modeled as a cooled flow, and please calculate the space between the ball and the table ramp, right? So we don't know the thickness. That means we don't know the thickness of the oil. So we know that a very important unknown parameter is h. We don't know the thickness, right, of the oil. So this is unknown parameters. Okay, so we go back to see our questions. And as you see, I highlight the sentence in here. The force diagram is very important for these problems. So we see how many force we have. So we can see the first we have the weight. This is the weight caused by the plate, right? And we know that the weight direction in here, we have the 25 Newton for the weight downward. Okay, and the second we have one shear stress force. So we have the shear force in here. So we're trying to only focus on the problems along the x-axis because we are trying to make the force balance along the x-axis. Why? Because in here we know that the constant velocity along the axis. So why the particle can move with the constant velocity? That indicates that the sum of external force along the x direction is equal 0. Sum of the external force along the x direction is 0. So that the particle can move with the constant velocity. This is Newton's law tell us. Okay, so we can write down some balance equation is a sum of the force along the x direction will equal to 0. So that means we should consider how many forces along the x directions. So the first, we have the weight. The weight is downward, right? But we know that we have, this is the incline table here. We have the incline table with the theta angle. So we're wondering to project the weight to the x directions. So we can draw the projection line in here. And this is also the theta angle. So we can have the force along x direction with these directions. Okay? So this is the weight. And we compute the sine theta. And we can project the weight contribute the force along the x directions. Okay? Another opposite direction force is the shear force, right? And I use the Fs. So these opposite directions go up, the upward. Okay? So if we wondering to go back to the force balance, we know that the F shear force should be equal to the W sine theta, right? Okay? Upward and downward along the x direction. But right now, we don't know what the F is actually. So we are trying to figure out, we based on the viscosity equation, because the viscosity equation can tell us the shear stress will equal to the mu multiply the velocity gradient. Right now, we know that the velocity of the plate. And we didn't know the how thickness of the oil. Okay, so if we can compute the shear stress, we can continue to compute the shear force is equal to the tau multiply the area, right? And right now the area is the interface between the plate and the table climb. Okay, so we just put the tau inside the equation. So we have a mu, and we have the velocity, and we have the thickness, and then multiply the contact area. Okay, and here is the contact area. We have the plate area in here. It's 1 meter square. And we have the theta angle, we have the velocity constant, and we have the dynamic viscosity. So right now, we only have the one unknown parameter is the h, the thickness we didn't know in here. So go back to the balance equation. The Vs, the dynamic viscosity multiply the area, and the V velocity divided h, okay, is our Vs equal to the weight sine theta, okay? And we reorganize the equation because we put the unknown parameter on left-hand side, and h will equal to a mu a velocity divided the w sine theta, okay? So we put all the number inside the equation. We have the 0.05 Newton seconds per meter square, and the area is the 1 meter square. The velocity is 0.02 meters per second constant velocity, and divided the w. The weight is 25 newtons, and the sine theta angle is 20 degrees. Okay, so you can check the unit dimensional balance. We cancel out the meter square, and the newton cancel out the newton, and there is a second in here, and we cancel out a second. So the final unit is equal to meter. It makes sense because we don't know the thickness of the oil. Okay, so you can just use your calculator to double check the final answers. Is correct or not. Okay, so for me, I quickly to calculate The answer is what 1.1 around 7 and 10 minus 4 powers, and the unit is the meter. And if you double check the answer showing here, compare with the top right corners, because the unit is different, the answer changes to the millimeters. So you can just check that they are the same solutions for these questions. Okay, so it's also a very simple exercise. I will just do some force balance. And the key knowledge is if we don't know the viscosity equations, we cannot compute the shear stress. And since you have the shear stress, so you can convert the shear stress to the force. And then you make the force balance to figure out how large the thickness of the oil. Okay, so this is a very good exercise. It depends on if you change the different incline angle, and if you keep the same velocity you want, and the thickness oil will change. Okay, so that's a case by case. If you're wondering to have the constant velocity larger enough, and what the parameter you should adjust. Okay, so you can adjust the different thickness and will have the higher speed of the constant velocity. Okay, so we mostly finished some ideas for viscosity equation apply the real case. So we're wondering to move to the next topic after we finish the shear force, and you understand how can we apply the viscosity equation to our problem. And the topic in the next is the surface tension. So you can see I write down some words and try to give the interpretation about the surface tension. The physical mechanism of the surface tension is based on cohesion force. Okay, as I explained before, which is an attractive force between like the molecules. Okay, so the same molecules we will have the coefficient force, and we can also call that is attractive force. And if you see this is the case in case, how can we figure out what is the surface tension we have in our problems? So the particle in here is the molecules, and you can see this is the water molecules. And molecules at the surface are actually pulled toward the center. Okay, pulled toward the centers because they have no liquid molecules above them. Because they're in the top, there are the airs. It's not the same molecules. So we don't have any cohesion force at the top. So this will pull the surface molecules to draw the surface inward and cause the liquid to seek the minimized areas. Okay, so that's the behavior between the surface tension and the phenomena trying to minimize the surface area is very important. So we are trying to do some exercise in the following slide, and you will know some phenomena related to the surface tensions. And this is very important why the water drop draw a spherical shape. Okay, so this is that's the physical phenomena for the surface tension. So I mostly write down some certain definitions of the surface tensions. As you can see in our textbook, the surface tension, we will use the sigma. So in difference compared to the mechanism, other mechanism class. The sigma in our class, we usually related to the surface tension. And the surface tension can be defined as the ratio between the cohesion force along the interface to the length of the interface. So you see the unit is the meter per Newton. It's a meter per Newton. So focus here, the force in here is a cohesion force, okay? So you should understand what is the force here between like molecules. And another definition for the surface tensions, we can also say the energies required to increase the surface area of the liquid divided the unit area. So that's why the phenomena, the surface tension, usually would like to minimize the surface area of the liquid. So if you would like to increase the surface area, you should have some required energies to support increase the area of the liquid. So if you based on the dimensional showing here, you have the joule per meter square. Okay, so but you just make the balance unit, they are the same. They are the same dimensional. Okay, so if you look some phenomena on the right figure in here, you can see the surface tension sigma decrease as the temperature increase. And at the normal room conditions, 20 degrees, you will have the 0.078 Newton per meters surface tensions. So this number, if you can remember, you can just take it into your mind to remember this number, around the 0.0728 Newton per meters. So there are physical phenomena associated with the surface tensions. So let's write down some, and I may take the interpretation right now. So the first one is weakening, and we can see which some phenomena material is an excellent fibers for the cold weather. Aerobic activity wicks perspirations away from the body. Okay, like the 冰风衣. Okay, and then capillary rise. Sometimes in our junior high school, we do some experiment laboratory, and we will try to see the phenomena. We call that the capillary rise. Okay, and then capillary rise is a liquid will rise in a small diameter tube. Okay, so in the following, we will try to do some exercise to understand how capillary rise we have in water. Okay, and usually in our natures, we always see the drop and the bubbles. It's because sometimes we see the water on the leaf is spits out. You can see the bubble in there didn't flow. Okay, and the excess pressures is the pressure inside the vapor pressure during the boiling is higher than the ambient pressure. And sometimes walking on water, 轻功水上漂, and we can see some strider can walk on the water also associated with the surface tension force. And the detergents also lower the surface tension waters. So can lower the surface tension of the water. And then the water can more easy to leak into the pore of the fabric. Okay, so that's some nature and in our life the phenomena always associated with the surface tension. But maybe some students sit here, you cannot understand why the surface tension can related to the physical phenomena showing here. So in the following slide, we have several exercises, and then you can try to understand how powerful of the surface tension in our life. Okay. So, and before we do exercise, also this is very important definitions. So the two words, we are trying to define the two words, the hydrophilic, okay, and the hydrophobic. Okay, we have two words, and we're trying to provide you certain definitions, and you can figure out why I call that the hydrophilic, also hydrobaric. And you see the title on the slide showing here, we try to compare the adhesion and the cohesions between the two materials. Okay, so hydrophilic, if we consider the water, okay? Because we wanted to discuss the water with a different material. And so the water will wet out on the surface when adhesion is greater than cohesion. Okay, so adhesion large in here, so the water cannot beat out. Okay, so in that case, the adhesion is larger than cohesion of the self molecules. Okay, so in that case, we say that the water loving, because the water loving the gas. Okay, and the hydrophobic, sometimes we call that the water hating. And you see a drop of the water will beat up because adhesion between the water and the Teflon is less than cohesion of the water. So the self-cohesion is bigger than adhesion. So that's why you put the water on the Teflon and you will see always formation with the bubble. Okay, you can see always the bubble water in Teflon material because the self-cohesion of the water larger than adhesion between the water and the Teflon. Okay, so for the water topic, the the two words, very important. The definitions of the hydrophilic and hydrobaric, the definition key knowledge is you just make a comparison between the adhesion and the cohesion. And you will have a different water loving and water hating behavior. Okay, so it's also related to the surface tension problem. Okay, so we just do a very quick exercise for the capillary actions. So the slide just show two examples. If you put the capillary tube into the water, and you can see some water level rising. Okay, the capillary tube put into the water, and you will see some water level increase. And that's because the adhesions between the tube and the water higher than the cohesions of the water. So there are some adhesion along the boundary will stick with the water. That's why the reason the water will rising. The boundary will stick the water, so the water will rising together. Okay, so that's we wondering to understand how high of the water level it is. Does it change by the different tube diameter? Okay, and the second knowledge, if we put the capillary tube in the mercury, but you actually see different phenomena in here because the mercury material didn't stick with the glass. So you cannot see the rising, it's just the falling. Okay, just the falling because the adhesions of the between the boundary is less than the cohesions of the mercury material. Okay, so maybe you cannot really understand, so we can do exercises, try to figure out the reason why. So you go back to see the figure in here, we actually know we have the rising high in that regions. And we assume this is a cylinder water columns. This is a cylinder water columns. So first we can compute how large the volumes for this column. Okay, the water columns, because we assume this is a cylinder's shape. So we can compute the area of the cylinder is we assume the diameter of the tube is the D. So the area of the columns, the water column, the area is equal to 4D squared multiplied pi, right? Okay, and the height of the water we didn't know, so we assume the height is the delta H. This is high is the water level rising high. Okay, we don't know. So we can put how can we compute the volumes? The volume should be equal to 4 over d squared, and the pi, this is the area. And the height multiply the height is equal to the volumes of the water. After we have the volume of the water, we can compute how large weight of the water. Okay, so we are trying to calculate the weight of the water. So W will equal to the rho is the water density, and multiply the gravity G. So this is a specific weight. Specific weight multiply the volumes. The volume here is the 4 over d squared pi delta H will equal to the total weight of the water. Will equal to total weight of the water. So we know that the downward force is caused by the fluid weight. Okay, right now our fluid is the water. So how about the upward force? So as you can see, the surface tension will acting on the circle's length. This is our water cylinders. And where is the surface tension? The surface tension will acting around the circles. As I provided the definition in previous slide, the surface tension is given by a ratio between the force along the interface divided the length of the interface. Okay, so right now the interface should be the surrounding circles, the length. Okay, so this is, we know that the weight will contribute to the downward force. So how about the upper force? The upper force will caused by the surface tension. Okay, so we first compute the sigma. We have the sigma. So we have the force caused by the surface tension. And we know that the surface tension is the sigma. And the radius length. The radius length is the d pi, right? So we have the d and we have the pi. This is the circle radius, the circle length. Okay, diameter multiply the pi. And because the surface tension with the angle between the vertical line is the theta, so we should project the surface tension into the vertical line. Okay, so we should multiply the cosine theta for this problem. We should multiply the cosine theta with this problem. So right now we can do some force balance. So I move this to other side. Okay, so right now we do the force balance because right now the water is steady state on that side. So the force should be the balance. So the up force is the 4d squared pi delta H rho Wg is the weight equal to the surface tension d pi and the cosine theta. Okay, so right now we are wondering to understand the relationship between the rising height and the diameter. The rising height and the diameter. So we are trying to cancel out some constant property. The pi cancel out. Okay, and so we have the 1 times d in here, so we don't have the square d. Okay, so we put the delta H, the rising height, on the left hand side, and we move all the parameter on the right hand side. Okay, so we know that the 4 times sigma surface tension cosine theta and divided the rho Wg and the d. Okay, so right now this equation is very good we can base on this equation to figure out if we change the different diameter, so how difference in rising height. Okay, so you can try to figure out if the diameter here is decreased, and then the delta H will increase a lot. Okay, and also you may have a different material in here, and because right now we consider the material is the water, if you change a different material, the density should be changed. Okay, and a different material will have a different rising height, and also different material with the boundaries will have a different surface tension. So it's a very good exercise. We can figure out how changes in diameter of the capillary tube result the different rising height of the material. Okay. So the right hand side, I put the one figure in here, and we can see the movie video to understand what's the rising height we will have. Most are my kids, and I cannot find the capillary rising height video. Okay, it's fine. I can have, maybe this one. Okay, good. So that the video show we put the different diameter tube into the water, and you actually see the different rising height, right? And the right hand side, the final tube in here is a small diameter. So you see that finally after the balance force, the rising height is much higher than others. Okay, this is a very famous laboratory experiment when I'm in the junior high school. We do that, the capillary rising observations. But when I'm a kid, I don't understand what's the reason we have a different rising height for a different diameter. Okay, so this is a very good exercise. We can understand how it's work of the surface tension. That's we tell you the capillary actions. And another exercise, why we always see the bubble, that's a spherical shape. Why they cannot change different shape, always the bubble shape. So that's some idea we can try to figure out based on this exercise. Okay, so and then you can see we're wondering to apply the force equilibrium to calculate the pressure rise inside the water drop. So our target is, we write down our target. Our target is a rise. The pressure rise, okay? This is our target, and we don't know what the pressure rise in our questions. And so there are some explain. You see the sentence, the pressure inside the water drop is higher than the pressure of the surrounding. If not, you cannot see the bubble. So the inside pressure should be higher than the environment, and to become the bubble shape. So please derive the formula for this pressure rise. Then calculate the pressure rise for what's the condition. We actually know the bubble, the diameter is 2 millimeters. So we should write down, we have the diameter for the bubble, the D is equal to the 2 millimeter, and then we convert the millimeter to the meter. So 0.2 and 0.02 meter. Okay? And we actually know the surface tensions for the water at the maybe room conditions. Okay? And surface tension is equal to the 0.073 Newton per meter. So you only have the two well-known parameter is diameter and the surface tension. So how can we apply the force balance to understand how large of the rising pressure. Okay, so the unknown parameter is the pressure here, and we didn't know. So right now we are trying to do some force balance. So the first, as you can see again, we have the if we cut the cross section of the spherical, and we know that we have the surface tension will acting around the circle radius, right? So we have some surface tension just act on the circle length. So what's the force caused by the surface tension? We know that the sigma surface tension we should multiply with the circle length. So we have the diameter d, and the circle length should be the d pi, right? So the circle length is the diameter multiplied by pi. But what's the pressure? We need to consider how large the pressure rise we have. And this pressure rise just acting on the circle area. So we have the circle area in here, and we have an inside pressure rise acting on the circle area. So that's the idea. We know that the rise pressures will equal to the force. Pressure force will equal to the rise pressure. Okay, acting on the circle area, right? But we didn't know the pressure rise. But we actually know the area circle is the 4d squared pi, right? Because it's acting on the yellow color in here is the circle area. Okay, so only unknown parameter here is the pressure rise. So we make the force balance. So the sigma, the surface tension force, sigma d pi will equal to the pressure rise multiply the 4d squared pi. And we can cancel out the sums the same. Okay, cancel out the pi, and we 1 times d and only 1. So we only have one unknown parameter. Put the unknown parameter on the left hand side, and then it's 4 times sigma divided the d. Okay, so we put all the parameter number 4 times sigma 0.073 Newton per meter divided the 0.002 meter. Okay, the dimensional is consistent. So we can directly compute the answer by calculator. So it's equal to the 146 and Newton per meter square, and this is relatively to the ambient pressure. So we say that the gauge pressure in here. Okay, so this is the pressure rising we require for have the bubble with the 2 millimeter diameters. So if we based on this equation, you should know if we require a smaller bubble, we wondering to have the smaller bubble, and the pressure rise in bubble will increase. So the smaller bubble size, we will require the higher rise pressure. Okay, and you can compare only a little bit pressure difference risings can support the bubble formation. Only a little bit pressure risings can support the bubble formations. Why I say this is a very small value? Because we know that the 1 ATM environment is equal to the 101.3 kilopar, right? And the par is equal to the dimensional Newton per meter square. So the number is very smaller compared to ambient pressures. So when we would like to support the bubble formation for the water, that the rise pressure requirement is smaller. We only need the very smaller amount of pressure rising in the water will become the bubble. Okay, so this is also very good exercise, and we can understand how it's work for the surface tension and why the reason we always see the water can become the bubble. Okay, that indicates the inside pressure is higher than ambient pressure, and the different inside pressure will form different size of the bubble. Okay, and the small bubble, we will require the large pressure rise. Okay, so that's a physical phenomena for the surface tension to understand why the water to form the bubble size. Okay, and then this is also another exercise. We, as I said, 轻功水上漂. Okay, and when we do the exercise laboratory experiment, and we put the needle on the water, but we can see the needle will floating on the water surface. So the question is, we wondering determine the size, how large the needles can be supported by the surface tension. Okay, so you just put different size for the needle and put on the water to see why the needle can floating, and you change different size. You can see some needle cannot floating. That means the surface tension can not support. Okay, so that's because we should determine the largest diameter of the needle. If you consider your needle material is the stainless steel with the SG, if you remember, the SG is a specific gravity. It's a very helpful property to convert the water density to the material, different material density. Okay, so that's our problem. So you can go back to see we have some video show if we put the stainless steel here, and you can see this is floating on the waters. But some people just use the finger to broken the balance. Okay, just broken the force balance, and then the water will flow outside, and then the needle will drop. Okay, again. So that's how can we see this phenomena? Because they do some force balance between the weight of the needle and the surface tension support upward, so that the needle can floating on the surface water. Okay, so if we go back to our exercise, we're wondering to explain the reason why and how the largest diameter, because the diameter size changes and the weight will change it also, but the surface tension support is a limit. So we should answer how large is the diameter we can support for our questions. So that's our questions. So before we do some exercise, we should double check some assumptions. That's showing here. I assume the needle is a cylinder shape. Okay, but actually it's not, because there are some different shape in the end of the needle. One point end is smaller, another is flat. Okay, so we neglect the end effects, and we trying to consider the condition is 20-degree water. So with the surface tension is 0.0728 Newton per meter. Okay, so when we do any exercise, we should consider how condition we have in the problem and how assumptions we apply in our problem. Okay, so go back to see how can we do some force balance. Okay, so we consider maybe this is my needle. Okay, and this is actually floating on the water. Okay, So how can we consider the force balance? I know that along the water surface, this is the water surface contaction interface with the water surface. I put the needle on the surface waters. Okay, and there will should be have some contact interface. We will have the surface tension force, right? Just support the needle upward force, and the needle itself have the weight, downward weight. Okay, so we should have some balance, force balance between the weight and the force surface tension. And we actually also know we should have some theta angle with the vertical line. But in our questions, if the theta angle is quite smaller, so we know that cosine theta will equal to 1 when the theta is close to 0, right? Okay, so we consider, we assume the cosine theta is equal 1, so we just neglect this effect. Okay, so let's go back to our questions. So how about the force contribute from the surface tension? So you should define the length you have. So we don't know the length, right? The length here of the needle we don't have because the question didn't support. The question here didn't support our information about the length of the needle. So I assume the needle length is the L. So the needle length is the L. So we know that the needle length is L, and so we have the 2 times sigma L, right? Because totally we have the 2 interface on the surface. So will contribute to the 2 times of the surface tension force. Okay, and how about the weight? And based on the weight, we should consider the cylinder volumes. Okay, so the cylinder volumes, we don't know the diameter of the needle, so we assume the diameter here is the D. So we can compute the area of the diameter D is 4/d squared pi, and the volume is the L, right? And we should multiply the material density. This is density is needle density, right? And this is multiply the gravity G. And if you didn't know the needle density, but we have the specific gravity here, the 7.7. So we can rewrite the equation to be the 4/d squared and the pi L, and the density can rewrite by the density water multiply the Sg values and multiply the gravity. Because the Sg is defined a ratio by the specific material density divided the water density. Okay, so that should have the force balance. So we put the surface tension force equal to the W, so we can balance the equations. The 2 times sigma L equal to 4d squared and pi L and the rho W Sg multiply the 1 gravity. So just based on this force balance, you know that we don't need information of the length, because the left-hand side will cancel out for the length of the needle. So this problem didn't affected by the length of the needle. Okay, so for this problem we didn't affected by the length of the needle. So only one parameter we don't know here right now is the largest diameter what we can have. Okay, so we put only one unknown parameter in here. D squared will equal to 8 times sigma, and divided the pi and the rho w s g and multiply the gravity. So you can put all the answer you know inside the equations. So we have the A times and the surface tension 0.078 Newton per second. And there is the pi, I use the 3.1415, okay? And the density here, I use the water is 1,000 kilogram per meter cubic. And the SG is no dimensional, so it's a 7.7. And the gravity, I use the 9.81 meter per second square. Okay, so you can do some dimensional balance, and you can compute the final answer you have in this problem. So I use my calculator quickly to check the number for this. And you can done by yourself and double check maybe something wrong. And this is a number is equal to the 4.45 and 10 minus 6 powers. And I guess that right now is dimensional equal to a meter square. And you take a root of the d square, and to see the answer is around 1.567 and the 10 minus 3 meter. Okay, and you can compare the units in here. They are the same numbers because we change the meter to the millimeter, so that almost the same values. Okay, so yeah, this is a very also good exercise, and we will very well know how can we apply the surface tension to our problem, and to explain the phenomena you see in the nature, why the 轻功水上漂 or some needle floating on the plate on the water, and you can determine how large the diameter of a needle we can put on the water and under the floating condition. Okay, so I guess the time is over, so maybe we stop here, and the next class we